So in this video we are going to discuss the questions which appeared in thermal and statistical physics in physical science examination that held in June 2011. Okay, the first question is: a cavity contains black body radiation in equilibrium at certain temperature T. The specific heat per unit volume of the photon gas in the cavity is of the form, so it's given that Cv, that is of the form gamma TQ, where gamma is a constant. The cavity is expanded to twice its original volume and then allowed to equilibrate at the same temperature. Okay, the new internal energy per unit volume is, okay, so the internal energy can be obtained, that is du, that is equal to Cv dt. So we are given the Cv, that is equal to gamma TQ dt. Okay, so that upon integration, but what we obtain is, it is gamma T4 by 4. Okay, so therefore the correct answer here is, it's option D. So let's take a look at the next problem. The statement is: consider a system of n non-interacting spins, okay, each of which has classical magnetic moment of magnitude mu. The Hamiltonian of this system in an external field H is given as minus mu I dot H, where I range from 1 to n, where mu I is the magnetic moment of the ith spin. The magnetization per spin at temperature T is, so that means we have to find the magnetization per spin, a ratio of this quantity. What is this equal to? Okay, because it's given to be a classical system, and the partition function can be obtained for the n spins Qn beta, that is equal to Q1 beta, that's a single spin partition function, and it's raised to power n. Okay, now Q1 beta, where Q1 beta is equal to exponential the minus beta times the interaction energy, which is minus mu h cos theta I. Now let's try to understand this problem. When a magnetic moment is placed in an external field, okay, so then it tends to align itself with the field direction. But in general, suppose this is a magnetic moment which is making an angle theta with the field direction, okay, and z is the field direction, so x and y, okay, and suppose the field is applied along the z direction, and when this external field is applied, it's not necessary that all the magnetic moment they will be aligned parallel to the field direction. So that depends upon the applied field strength. Okay, so the angle theta, this is it represents the angle which is made by a magnetic moment of one single dipole, okay, with the magnetic field. So the z component of the magnetic moment mu z, that is equal to mu cos of theta. Now this angle theta, it can take all possible value which range from 0 to 2 pi, okay, for all sort of possible combinations. Okay, so what we are going to do is, basically we will consider a solid angle by assuming this to be a three-dimensional problem. So we will consider a solid angle, and then we will try to evaluate the partition function. Okay, so before that, the net magnetization along z direction is given by net magnetization along z direction, because mu z, that is equal to mu cos theta, that represents the z component of the magnetic moment of one single dipole that's having angle theta with respect to z. Okay, so mz, if I denote the net magnetic moment as mz, this will be equal to n and average value of this mu z component of the magnetic moment. Okay, because of the a large number of values that are feasible for theta. Okay, so that is equal to n times average value of mu cos theta. Okay, now here we will apply the definition of the average value of a quantity. So this is equal to, in principle, n and all possible value of theta, and then the physical quantity, that's mu cos theta here, mu cos theta, okay, then the probability, okay. So exponential, because the interaction energy of a dipole with field, that's minus mu dot h, okay. So let me write it here. The interaction energy of a dipole, that is equal to minus mu h cos theta r, okay. So here exponential minus beta multiply by the mu h minus mu h cos theta, so that will give us exponential beta mu h cos theta, okay, and then divided by summation over theta I exponential beta mu h cos theta, okay. And now we are going to rearrange the terms so that we can obtain a final expression, desired expression. So n, and inside the bracket, so I'm going to rearrange this entire expression, this expression I'm talking about, okay. So I will write first the term in the denominator 1 upon summation over theta I exponential beta mu h cos theta as it is. Now the terms in the numerator, then summation over theta I exponential beta mu h cos theta, and then here I'm going to introduce a factor of beta, so I'm multiplying by with the beta and also dividing by beta, so ultimately the expression remain unchanged, okay. And then what is left is, that is mu cos theta, okay. Now I'm claiming that this is equal to, this is, so I will take this beta outside, okay. So this is equal to n by beta, and inside the bracket we are left with curly h of ln q1 beta, where q1 beta, that is given by this expression, okay. So when we take the differential of q1 beta, ln q1 beta with respect to h, we must obtain this expression, and that is in principle that definitely you will obtain this expression, okay. So let me call this as equation 1, this as equation 2, and this final result as equation 3. So therefore from this equation, from equation 3, we notice that the magnetization per spin, that is equal to simply 1 by beta curly h of ln q1 beta. So now the problem is left, that is to determine what is q1 beta, okay. So if somehow we are able to determine q1 beta, then we will be able to determine the magnetization per spin, okay. So let's take a look at how we can determine q1 beta. So let me introduce a page and then we will continue, okay. So because theta I, now the argument that we are making here is that because theta I can take any random value, okay, that is we will consider a 3D distribution, okay. So we will consider an elemental solid angle, and then we will try to integrate over the entire 3D picture. So therefore q1 beta can be written as, therefore q1 beta, that is equal to 0 to 2 pi and then 0 to pi exponential beta mu h cos theta and then sin theta d theta and then d phi. So integration over d phi, that's from 0 to 2 pi, so that will give us a factor of 2 pi. So I'm keeping this factor outside, that's 2 pi, and then now it's only the integration over the theta. So 2 pi 0 to pi exponential beta mu h cos theta d theta. Okay, so let me call this as equation 4. Now here what I'm going to do is I will consider we are going to replace the variable. So we will consider that let x is equal to minus cos theta, so that dx is equal to sin theta d theta. Okay, we are intentionally taking a negative sign here. So, okay, so this is equal to this one. Okay, so as x goes to 0, sorry, it's already in theta. So when theta goes to 0, then x goes to, when theta is 0, x is minus 1. Okay, and when theta goes to pi, x goes to plus 1. Okay, so with these changes, now equation 4 can be rewritten as q1 beta, this is equal to 2 pi minus 1 to 1 minus 1 to plus 1. Okay, exponential minus beta mu h x. Okay, and then dx, and that is equal to 2 pi as it is, and integral of this exponential minus beta mu h. Okay, that is exponential minus beta mu h, exponential minus beta mu h x upon minus beta mu h from minus 1 to plus 1. Okay, so after substituting the value of x in of the limits, so we obtained this result. So result to be equal to, this is equal to 2 pi upon beta mu h, and inside the bracket we will have exponential beta mu h minus exponential minus beta mu h. Okay, and this is basically equal to twice sine hyperbolic beta mu h. So we will have a factor of 2 outside, and then it the expression for the q1 beta reduces to q1 beta is equal to 4 pi upon beta mu h sine hyperbolic beta mu h. So that's the expression for the partition function. Now we have determined the partition function for this system. Let me call this as equation 5. Okay, now we will make use of equation 3 and 5. So what is equation 3? That connects the mz with the partition function, and partition function. From here we will be able to determine mz by n. Okay, so now equation 3 and equation 4. So let me introduce another page. It's a slightly lengthy example. So now equation 3 and 4, equation 3 and 4 implies mz equal to n by beta, and then curly h of ln q1 beta. Okay, so now substitute the value of q1 beta, so this becomes n by beta curly h of ln 4 pi upon beta mu h sine hyperbolic beta mu h. Okay, now we have to differentiate it basically. Okay, so this is equal to n by beta outside, n by beta, and then curly h of this quantity. So 1 divided by this entire expression. So 1 divided by 4 pi upon beta mu h into sine hyperbolic beta mu h. Okay, and then again curly h of 4 pi upon beta mu h sine hyperbolic beta mu h. Okay, and this is further equal to n by beta into beta mu h upon 4 pi, and then sine hyperbolic beta mu h, and then its differential. So let's see what is the differential. So this will be 4 pi upon beta mu, that's constant, so I will take it outside, 4 pi upon beta mu. Okay, and then inside we are having sine beta mu h upon h, its differential. Okay, so its differential with respect to h will be, so 1 by h as it is, and then differential of this quantity, so that is cos hyperbolic beta mu h into multiply by beta mu, so it's a separate. Okay, beta mu, and then differential of 1 by h with respect to h, so that will give us minus so I have already taken minus here, so minus 1 upon h square, and then sine hyperbolic beta mu h as it is. Okay, so this is now we will see that when we will multiply this the external term with the internal terms. Okay, so we will obtain two terms, and some of the terms will cancel, and after cancellation what we obtain is, I am writing that expression directly here, so this will be n mu into, in the bracket we will have cos hyperbolic beta mu h. Okay, so all the rest of the term will cancel with each other, so 4 pi will cancel with the 4 pi, and this beta mu will cancel with beta mu, and h inside we will have h, so h will cancel this h. Okay, and then and also beta will also cancel with this beta. Okay, so n mu is left, so that's why n mu outside, so inside we will have cos hyperbolic beta mu h upon sine hyperbolic beta mu h, and then in the second term we will only left with the minus 1 upon beta mu h. Okay, so this is equal to n mu cotangent hyperbolic beta mu h minus 1 upon beta mu h. Okay, so this implies magnetization per spin, that is mz by n, that is equal to mu times cotangent hyperbolic beta mu h minus 1 upon beta mu h, or this is equal to mu, it's a Langevin function basically, beta mu h. Okay, this is our final result. Okay, so let's take a look at the options which are given to us. This is, yes, this is option B here. Okay, so mz by n, that is equal to mu cotangent hyperbolic beta mu h, which is mu h by kt, minus beta mu h, which is minus kt by mu h. So therefore B is the correct option here. So let's continue with the next problem. So basically this is related to Bose-Einstein condensation. So the statement is, consider an ideal Bose gas in 3 dimension with energy momentum relationship of the type E is equal to P power S. It's not 5 but it is S basically. Okay, with S greater than 0. The range of S for which this system may undergo Bose-Einstein condensation at non-zero temperature is. Okay, so let me emphasize on one point here. Basically these results, they are based upon some mathematical expressions. Okay, so it's not possible to discuss all those things here. So what I'm going to do is, I'm going to leave the expression at a certain point, and then at that point I will discuss the important results based upon that expression. Okay, so here so we will start from the number of states in 3 dimension. number of states in 3 dimension with momentum less than equal to p. So that is they are given by omega p, that is equal to the phase space volume b into 4 by 3 pi p cube upon h cube. Okay, so let's call this as expression 1. Okay, now similarly the number of states in the range from p to p plus dp. Okay, from p to p plus dp. We are doing this exercise because basically we want to determine the number of particles in the all excited state except in the ground state of the bosonic systems, and for that purpose we need to know the density of states basically. Okay, so for 3D system this is equal to omega dash p, basically that is equal to d omega p upon dp into dp, and after differentiating this expression with respect to p, we obtain this is equal to 4 pi v upon h cube p square dp. Okay, now we are having a relationship which is E, that's proportional to p power s. This implies E, that is equal to a p power s, where a it's a constant of proportionality, you can say constant, and it's also given that s is greater than 0, it's given. Okay, so from here p equal e upon a power s, and then dp will be 1 by a power s, 1 by s e power 1 by s minus 1 de, or we can write dp equals to 1 upon a power 1 by s multiplied by s e power 1 minus s upon s de. Okay, so therefore the density of states are in the energy range e to e plus de, that is equal to 4 pi b upon h cube e by a power 2 by s a power 1 by s and then e power 1 minus s upon s into de. Okay, or this can be, all these terms can be rearranged, 4 pi b upon h cube 1 upon a power 3 by s into s, and then energy power 2 by s plus 1 minus s upon s and then de. Simplifying this result, we obtain this is equal to 4 pi b upon s h cube a power 3 by s e power 3 minus s upon s de. Okay, so let's call this as equation 3. Now the number of particles n that a system can accommodate in the higher excited states. We are not talking about the ground state, but we are talking about the particles in the excited state, because in Bose-Einstein condensation, when the condensation takes place, the largest number of particles they accumulate in the ground state, and the correspondingly the occupation in the excited state, that should be as small as possible. Okay, so here this expression n, which gives us the number of particles in the excited states, basically this should have a finite value and small. Okay, it shouldn't diverge actually, so that will allow us to fix the value of corresponding value of s. Okay, so that is 0 to infinity the number of states de divided by, that's a distribution function, exponential e upon kt minus 1. Okay, and when you substitute the value of density of states, so this expression become equal to 4 pi v upon s h cube a power 3 by s 0 to infinity, okay, and e power 3 minus s upon s divided by exponential beta e minus 1. That's a distribution function for the bosonic particles. Okay, so let me call this as equation 4. In fact, it's already given that s is greater than 0, but if you just take a look at, if you substitute the value of s is equal to 0 here, then this integral it diverge. Okay, so that means s is equal to 0, it's not a valid solution, so it's show that s is greater than 1. So that's the first point that we notice from this integral. Okay, now the important point is that here we have to ensure that integral it doesn't diverge. Okay, in case the integral diverge, then so that means that value of s will not be valid. Okay, so for s is equal to 0, for s is equal to 0, equation 4 it diverges. Okay, so that means s is equal to 0, it is not allowed. Okay, now when we take s is equal to 1, the corresponding integral reduces to, for s is equal to 1, corresponding integral reduces to, I am keeping all rest of the terms as a constant. I am merging all those terms in the constant c1, 0 to infinity, and it is e square upon exponential beta e minus 1 dE. Okay, so it can be shown that for the mean s is equal to 1 also, this integral it also diverge. Okay, that this requires rigorous mathematics, and this cannot be discussed here, but it's because it's a standard result and you can just remember it. Okay, so for s is equal to 1, this will diverge, whereas when s is equal to 2, the corresponding value of n, that is equal to c1 0 to infinity e power 1 by 2 upon e power beta e minus 1 dE. Okay, so it doesn't converge, it doesn't diverge, it converge. Okay, and for even for s is equal to 3, one can easily show that the equation 4 diverge. So that means out of the given options here, the the correct one is option A here. So let's take a look at the last problem. The statement is, a particle is confined to a region x greater than 0 by a potential which increases linearly as ux, that is equal to u naught multiplied by x. The mean position of the particle at temperature T is, okay, so here the mean value of a physical quantity, as the general expression that we have used many times, so that is given by the physical quantity itself and then the corresponding probability distribution, okay, over the relevant range, and then divided by px dx from within appropriate limits of integration. Okay, so because here we have to determine the average value of the position basically. Okay, and for the particle, okay, so that is equal to 0 to infinity, because this range of integration that's specified here, it's from 0 to infinity, and then exponential. It's the potential contain only one terms in x, so therefore we only need to consider the only one term in the moment integral involving momentum. So exponential minus p square upon 2m kt dpx or dp you can say. Okay, and then the other integral involving the the potential energy 0 to infinity and x exponential minus u naught x upon kt dx, and the denominator again the probability. Okay, so 0 to infinity. So basically the expression for the probability we have split it into two integrals basically, okay, the space and the momentum integral. So okay, in the denominator again we will have exponential minus p square by 2m kt dp, and 0 to infinity, sorry, exponential minus u naught x upon kt dx. So basically these two will cancel with each other, okay, and we are simply left with 0 to infinity x exponential minus u naught x upon kt dx upon 0 to infinity exponential minus u naught x upon kt dx. Okay, so here we will make a substitution and then try to solve this integral. So the substitution that we are going to make here is that let u naught x upon kt, this is equal to a new variable t, okay, so that as x goes to 0, t also goes to 0, and as x goes to infinity, t also goes to infinity, okay, and from here also we note that x is equal to kt upon u naught, okay, kt upon u naught multiplied by t. So from here dx also become equal to kt upon u naught into dt, okay. So with these changes in this expression, while after substituting all these things here in the expression, we obtain that average value of x, that is equal to so here when we'll substitute x, so we will have a factor of kt by u naught from here, and then while substituting dx again we'll have a factor, same factor, okay. So here therefore in the numerator we will have kt upon u naught its square, okay, and then 0 to infinity t exponential minus t dt, okay, divided by kt upon u naught 0 to infinity exponential minus t dt, okay. So this is a basically gamma function whose value is gamma 2, which is equal to 1 factorial, that means 1. So this will yield 1, and this will also yield a factor of 1, okay. So that means at the end we are left with mod of mean value of x is equal to kt upon u naught, okay. So therefore A is the correct option here.